All right, so chapter 18, nuclear chemistry, and we obviously talked about some different types of particles. And remember, there are the alpha particles, which has a 4 and a 2. It is also helium is sometimes used for our alpha particle. It's the one that has the major sort of change that occurs. We also have beta particles, 0, -1, which is basically an electron. So again, it does have kind of two different sort of symbols that are commonly used. We have the gamma ray, which is basically 0 and 0. As we talked about last time, right? Top number is our mass number. Bottom number is our atomic number, which is the number of protons. Mass number is the number of protons and neutrons there are in an atom. Some other ones, a proton, sometimes used as obviously AP, are hydrogen. A neutron, which is that guy. And we also have like a positron, which basically shares the same sort of symbols as the beta particle, but it is a positive guy. As we talked about, each of these sort of particles are basically sort of emitted in the process of converting certain particles within the nucleus. So protons to neutrons, neutrons to protons, and these are sort of the leftover stuff that gets emitted as a result of those sort of processes. So because we are changing protons, which is the atomic number, we do have a change in the elements that we see. So there is no conservation of elements. So as we talked about, to balance nuclear equations, you pretty much just need to make sure of two things. The mass number on the left, when you add up all those mass numbers, will equal the mass numbers on the right. And when you add up all the atomic numbers on the left, they need to add up to all the atomic numbers there on the right-hand side. Usually, if you have something missing in an equation, it is the atomic number in the periodic table that will help you basically determine what is missing. It could also be a particle like one of those guys up there, you know, if it doesn't maybe match an actual element or anything like that. The other thing we talked about is some of the nomenclature that goes with sort of the words that we see. So any type of particle goes through some type of emission, an element that goes through emission, those particles end up on the product side. If this is emitted, it's on the product side. If something is like an electron capture, that would be on the reactant side, that particle. And if something gets bombarded, that's usually on the reactant side. So those are sort of the common language words that we see. Any questions on that stuff there we talked about last time? All right. So I think this is where we left off. So why don't we try this one here, write the nuclear balanced equation for the positron emission of potassium-40. See what you come up with. Might want a periodic table, if you can find one. So potassium-40, that 40 is the mass number, which should go up on top. We could get the atomic number there from the periodic table, which is 19. This is going to go through a positron emission. So emission means our positron particle there will be on the other side. And you could use either the beta symbol there or the E if you like. Remember, we're looking to add up to the same number on each side. So we got 19 there. We got 1 there. That means our missing element's 18. If we go to periodic table, number 18 is argon. Here we got 40 up on top, 0 here, which means 40 would be right there. That's 40 up on top and 19 on the bottom. Any questions on that one there? Remember, it is the atomic number that will tell you what element you are dealing with. Yeah. All right, so let's try a few more here. I think you got, hopefully, the 3. All right, why don't you give these a go, see what you come up with, write the nuclear equations for each of these here. All right, let's take a look, see how you're doing. We'll start with the first one, which is uranium-238. Again, that's going to be the mass number. We get the atomic number from the periodic table. That looks like a 92. Looks like a winner there. That's going to emit an alpha particle, which you could do that, or again, you could use helium if you wanted to instead. Again, we're going to be looking for missing atomic number first. We have 92 on the left, 2 on the right, so like a 90 would be good. Going to periodic table, we find number 90 is TH. And now for our mass number, we got 238 on the top, 4 on the right there. That's a 234, I think there. Questions on that one? Next one is neon, 24, which is our mass number. Our atomic number from the periodic table there going to be 10. Once again, it's an emission. And we will have our beta particle, which again, you can use the beta symbol, or you can use the E if you'd like. In this case, because that is -1, we're going to bump up to 11 there on the right-hand side to give us 10 when we add those numbers together. And that would be sodium. And up on top there would be 24 in that particular case. Looking at the next one, which is nitrogen 13. Nitrogen 13 up on top, 7 from the periodic table. Going to give us a positron emission, which is basically like a positive electron. So we got that going on there. So we got 7 on the left, 1 on the right, leaves us a 6 left over, which looks like that should be carbon, I believe. And a 13 on top will also give us 13 on both sides. And lastly here, beryllium 7. Beryllium is number 4, looks like. This is going to be an electron capture, so that means that our electron will actually be on the reactant side, and since it is an electron, you should use usually the E there instead of the beta symbol, so there's no misunderstanding. And that is going to get us a 3 left over on the bottom there. When we take 4 plus -1, gives us 3. That will be lithium if we go to the periodic table, and 7 up on top. Yeah. Any questions on balancing nuclear equations? So like I said the other day, some addition, a periodic table, and you should be pretty set, I think, to balance these guys. Any questions on any of those? Okay. Then let's talk a little bit about stability. And one way that we look at stability of a nuclide is by what is referred to as the N to Z ratio, and that is the neutron basically to proton ratio there. Neutron really to proton, as Z is our atomic number kind of symbol there. And if the ratio of the neutrons to protons is an important sort of aspect of stability, now there is sort of an acceptable ratio of neutrons to protons, which we'll look at in just a second. But if we sort of fall a little bit too high from that sort of accepted ratio, it will be really unstable at that point. And what will happen is it will go through really radioactive decay to try to bring itself sort of back down to being more stable. And in this case, neutrons are converted to protons via a beta decay. So if you sort of calculate the neutron to proton ratio and it's too high, that sort of nuclide will go through beta decay. And what that should do is it may not make it perfectly good ratio, but it should move it back down to maybe a more acceptable sort of ratio, a little bit more stable ratio. The opposite can also happen, obviously, if you calculate the neutron to proton ratio and it is too low. We will convert some protons to neutrons via really 2 sort of processes. A positron emission or an electron capture can happen. Also through an alpha decay, but not as efficient. So for us, we're not going to really follow the alpha decay. So if our ratio is too low, we're going to roll with one of those 2 things basically occurring: positron emission or electron capture. Now, just to sort of show you that there's actually no difference there, we had beryllium 7 and 4, I think is what we just did. So that one that we just did, which was 7 for beryllium, and we did an electron capture, which got us to 3, 7, and lithium. So if we did the electron capture, that is what we would get. if we did a positron emission starting with the same guy there, a positron emission would mean we would come out on that side. Now our missing guy is 3 or pi 7 up on top, and it is the exact same thing. So both of those processes will actually lead to the exact same formation of your new nuclide. So you could do either one. They both will obviously hit you with the same guy at the end there. If you do a positron emission or an electron capture, will result in the same thing. So we will perhaps get something that is a little bit better of a ratio, but it will not be perfect. And if you have these type of problems, you don't need to kind of keep going until you get a perfect ratio. So usually just one of these sort of emissions is sufficient. So let's look at what is sort of considered good or bad sort of ratio. And this is what we got going on here. This is sometimes referred to as the valley of stability. Some books and people call it the belt of stability. And that is where we have really a stable sort of ratio of neutrons to protons. So when we're talking about being too high, that means we fall sort of on this side of that belt. And as we go through our beta decay, it will kind of bring it back down to a more acceptable level. If we're a little bit too low, we're kind of on this side of it. And what we just talked about there, the electron capture or the positron emission, will kind of fix our ratio and kind of bring us back up to that belt of stability. It is broken up by, in terms of the acceptable ratio, the atomic number. So the atomic number, whatever sort of element you're looking at, if it is somewhere between 1 and 20, the acceptable ratio is basically a ratio of 1. And if it's somewhere between 20 to 40, it is 1.25. 40 to 80, it is 1.5 is the acceptable ratio. And really anything above 84, as we talked about the other day, is pretty much not going to be stable. It's going to be radioactive and stuff of that nature. There is sort of a grayish area that sometimes comes about, as that's 20 and that's obviously 20, and they both have different ratios. And obviously that's 40 and that's 40. So there is those sort of grayish areas where sometimes they'll go, well, it's close enough, you know, to one versus the other, and they'll be stable. So for us here in class, we're going to just make these really just hard cutoffs, and either it is that number is too high or too low, and we'll kind of try to take as much of the gray area out of it. But be aware, sometimes in books they'll go, well, you know, it's kind of in that grayish area between the two, and it's still okay, even though it's technically higher than the first one. Maybe it's lower than the second one. So we'll try to use these as sort of hard cutoffs. And I'll try not to give you one that's on the cutoff number there. So it could either be that number or it's too high or too low. Any questions on that there? All right, so why don't you give one a try here, maybe. Go. Magnesium 22, is it stable? If not, write the reaction for the decay process that it will undergo. In case you don't have a periodic table, magnesium's number 12 on the periodic table. Okay, let's take a look. So first off, we want to really figure out what is the N to Z ratio here. So magnesium 12 on the bottom, 22 up on top. So our protons is going to be equal to our atomic number. Remember, our neutrons is our mass number minus our atomic number, which in this case is 10. That gives us an N to Z ratio of 10 divided by 12, and that's going to give us like a 0.83, I think. This is a 1 through 20 situation where the acceptable ratio is 1 in this case, which means I feel we're a little bit too low there. So because it is too low in this case, it will go through one of those two options that we talked about, either electron capture or a positron emission. So if we did our equation with the electron capture, that will give us an 11 on the bottom, which is sodium from the periodic table, and a 22 up on top, or a positron emission, where we will also yield 2211 and sodium in this case. Yeah. Question on that. Now, if we look at what happened, we were a little too low in terms of where we were originally. What we just formed by coming through this sort of decay process is sodium 22. That has 11 protons, and neutrons would be 22 minus 11, which is 11, which means its N to Z ratio is now 11 divided by 11, which is 1, and that actually was pretty good. That got us to a really stable sort of situation in that case. Again, it will not always hit exactly stable perfect, but it should definitely move you towards the right direction in terms of that ratio. Any questions on that there? Obviously, if you're moving the other way, you did something wrong, probably with the math, I'm assuming, or you did the wrong decay process. Any questions on that one? All right, let's try one more here. Krypton 85. Again, is it stable? And if not, write the reaction for what will happen. Krypton, I believe, is 36 there on the periodic table. This one, so once again, we're going to start with our numbers here. So that's going to be 85. That's going to be 36. We're looking for the N to Z ratio. So our protons would be 36. Once again, here our neutrons would be our mass number, which is 85 minus 36. I think a 49 is in order there. That gives us an N to Z ratio of 49 divided by 36. Gives us a 1.36. This is a 36, which falls between the 20 to 40 sort of category. Accepted ratio about $1.25 there. So that looks a little bit on the high side here. So we need to kind of bring that ratio down. And again, when we're on the high side, it's going to bring it down by going through a beta decay, I believe. And that means that we will end up with something like that. And we got a negative one there, so that's a 37, I believe. And we'll go to the periodic table, and 37 there is RB. Up on top is going to be an 85 in this case. Yeah. So in this particular case, if we sort of analyze where we ended up, our N to Z ratio for this guy would be 85 minus 37. Going to give us an error. Going to give us a 48 divided by 37 in this case. So divided by 37 gets us to kind of like a 1.3-ish, 1.29, bringing us closer. But again, in this particular case, not perfect. And you might not always obviously get a perfect ratio afterwards. And you don't need to continue on until you get a perfect ratio. You could just stop after that first reaction. Question on N to Z stability here. Okay, we're going to continue on here. So we're talking about stability, and one very common way to look at stability is what we just did, which is the N to Z ratio with the actual number of protons and neutrons that are involved. There are some other things that sometimes we look at in terms of stability. Most stable nuclei will have sort of an even number of protons or neutrons. And we can see from this table, for example, 157 stable nuclei, when you have kind of even of both of those things, are protons and neutrons. So that's like the best situation is those protons and neutrons being neutral. All right, so our positive neutrons and protons is the most stable. Next best situation is kind of even number of protons, odd number of neutrons. It drops significantly there down to what we got there, like 53. Next best case, odd and then even neutrons. And really, as you can see, the worst sort of situation is odd and odd. So if you have an odd number of protons, odd number of neutrons, that is sort of the not greatest situation there for nucleides. If the total number of nucleons, and nucleons is a word that you kind of hear a lot here in nuclear chemistry. A nucleon basically means the particles in the nucleus, and that basically is your protons and your neutrons. So if the total number of nucleons do add up to some magic numbers, then the nucleus is more stable, kind of like noble gas configuration with electrons. You know, if you hit that kind of noble gas, you're in stable configuration. So things are most stable when either the neutrons or the protons are 2, 8, 20, 28, 50, 82, and your mega number of 126 there, in case you want to play it later, are sort of stable arrangements. So I say most people will look at kind of the N to Z ratio, this sort of situation here, and a little bit later on we'll talk about binding energy, which is kind of a third thing that people kind of look at in terms of stability. And in most cases, you can make a pretty fair guess as to what's going on. So let's talk a little bit about then a decay series. And a decay series is one where we start with something that's radioactive, and then it will sort of spontaneously, if you will, kind of go through the decay process. And then we'll continue this decay process, which is sometimes referred to as a decay series, when you have multiple, obviously, processes occurring at once, until it pretty much hits something that is stable. And so there's a couple different ways that you could kind of do a decay process. You can, if you're looking at alpha and beta decays, you can just do some math, if you will, from the mass number and the atomic number. And if all you're interested in is maybe just the end product there, of what you get after a series of decay processes, you can count up the alpha decays and the beta decays. And for every alpha decay, you subtract 4 from the mass number. And from the atomic number, you subtract 2. And then for the atomic number, for every beta decay, you basically add 1 back, because that's the -1. So you kind of add 1 back, and that'll get you what's at the end. The other way you could do it is basically just like what we did with balancing equations, and just write each equation out, and it'll give you obviously every step. So for example, we took our friend uranium-238, and we were going to do like an alpha decay, a beta decay, a beta decay, and then an alpha decay. We'll just do a short little run there. And if we wanted to kind of know what was going to happen in each of these processes, we essentially can just write our reactions like we did before. We could go to uranium-238, and then obviously go to the periodic table and look up uranium, which is 92, I believe. And basically the first thing that would happen is it will go through an alpha decay. And that means we'll have a 4 and a 2 and an alpha here to take care of that guy. That means the first thing that's going to form is 90 and 234. And again, 90 there is going to be TH. Then what's going to happen is really your product of the first one will be the next guy that will go through a decay process. This is what is referred to as the parent nuclei. This is the daughter nuclei, what is formed as a result of that decay process. So then this guy here will go through the next decay process, which in this case happens to be a beta decay. And what will happen is we will have our beta particle given off on the other side. And in this case, we need 91 on this side and a 234. 91 on the periodic table there is our PA. Then this guy will continue on through the process here and also go through a beta decay, and that will give us a 0 minus 1. And in this case, we'll be back up to 92, but with a 234 in this case. And that 92 is going to take us back to uranium at that point. And then our product here will go through the last decay process there in my short little run here, which is an alpha decay, a 4, 2, and an alpha. That's going to get us to a 90, and that will get us to a 230 there. And again, a 90 is going to be, where's number 90 there? TH. And that would be obviously the end result of that short decay process. This process would continue obviously until something sort of stable gets hit at that point, right around lead when you get down to that point. Now, what we were talking about earlier is you can, for every alpha decay, subtract 4 from the mass number and 2 for the atomic number. For every beta decay, you could add 1 back there to the atomic number. So if maybe you were just interested in like what you get at the end here, you could just do that by really just subtracting the numbers. So if we took 238 and 92, we have two alpha decay processes, which means we're going to subtract 4 and 4, and also 2 and 2 from the atomic number. And we have 2 beta decays, which means we will add 1 back to each of those. And if we do that math there, that's going to be 234 and 230 for our top number. That's going to be 92 to 90 to 88. Add 2 back gets us to 90, and we are in business there. So if you're just sort of interested in the end result and it's just beta and alpha decays, you could just kind of subtract off those values and it'll get you the end one. If you want to be maybe a little safer so you don't make any math issues, maybe step by step is a good way to go, and you could just use that to check yourself at the end to make sure you got what you should want. But again, that is sort of how you would do a decay process. Any question on that, or decay series? Okay, so looking at something like uranium 238 there, it actually veers off there towards the end and ends up with 2 different sort of decay paths, but they all do end up at the same location down there. And obviously, I think we only took it to about here in terms of where we went. Obviously, you can see it will continue down that path. And again, at some point, it will sort of vary a little bit. But the end result is it will stop when it does hit that sort of stable guy at the end. So let's talk a little bit about kinetics and radioactivity. And all radioactive decay follows first order kinetics. And kinetics is, right, how fast or slow a reaction takes place. The good news is it really is the same sort of kinetics that you learned in the kinetics sort of chapter. They will use some different sort of symbols sometimes because it's nuclear chemistry, but it ultimately is the same 2 sort of equations. To remind everybody about the 2 equations for first order kinetics, that basically means that you take the natural log of A is equal to the natural log of A naught minus KT, where the half-life is the natural log of 2 divided by K, which is the rate constant. In here, they will use some different symbols sometimes, like you can see on the bottom there. They'll use N for nuclide instead of concentration. They will also sometimes use K. They'll also sometimes use the lambda symbol for the decay constant. They call this the decay constant in nuclear chemistry, but it's the same thing as the rate constant in kinetics. And a reminder that when we see T here, that's actually time. So that's not temperature, but that's actually time. So again, sometimes even the decay constant is a lambda sort of symbol is sometimes used for it in nuclear chemistry because they like to use their own sort of things. All radioactive decay follows that first order kinetics, which means if you take the natural log of A versus time, you will get a straight line where the slope of that line is equal to the rate constant or the decay constant in this case. And that is because if you rearrange the first order equation, natural log of A is equal to minus KT plus the natural log of A naught. This is written in the form of a straight line, y equals mx plus b, where on the y you put the natural log of A, on the x you put time, basically. And the slope there will equal negative, again, of the decay constant in this case, which is really very similar to the rate constant. It's kind of the same idea. Also a little bit different than sort of traditional kinetics. In traditional kinetics, when we put our values into this equation, which is sometimes referred to as the integrated rate law, We oftentimes use molarity and concentration, which you can still use. But in nuclear chemistry, we do use a lot of different sort of units. And it really doesn't matter the units that you put in here, as long as they're the same unit. So you can do like grams and grams on both sides. You can do milligrams and milligrams. You could also do rates of radioactive decay, like counts per minute or something like that, is sometimes used. By the way, this first A is the final concentration. This A with a knot is the initial, yeah, concentration. And again, the K is our decay constant. This is also sometimes written 0.693 because that's what you get when you take the natural log of 2 on your calculator. Yeah, so that is the same thing. Half-life, right, is the time it takes for half of whatever you started with to go away. Yeah, so if you had 10, the time it takes for you to end up with 5, and after that, the time it takes for you to end up with 2.5, and then I need a calculator after that point, but I keep going by 2, and you could cut it down. Any questions on that there? All right, so there again, like I said, sometimes they will use these N's for nuclides, and again, that is the decay constant, and which is basically kind of, again, the same thing as the rate constant. This is also a common graph for first order kinetics, and what we see is over time it is decreasing the concentration of our nuclei, which is what we expect because it's decaying, right? So we're losing it over a period of time. Now these are some half-lives of some various nuclides, and as you can see, half-life, which again is that time it takes for half of whatever you started with to sort of go away, can be really long, can be really short. Clearly here we have uranium-238, which is like 4.5 times 10 to the 9 years, which is a super long time for one half-life basically to occur. Unfortunately, I don't think any of us will live through one half-life, right? Carbon-14 is 5730, but there are some half-lives that are obviously very quick. As you can see there, 55.6 seconds. It's like every 60 seconds, is half of it's gone. So it goes away very, very fast. As we'll talk about a little bit later on in the chapter, obviously, if you're using anything like for medicine, right, you would want a very short half-life. For example, it does vary even depending on the type of isotope that you're using. Different isotopes, even of the same element, are different. For example, copper 64 is like 13-hour half-life. Copper 68 or 68, I think it was, it's like 3 days. So, you know, there's a big difference in terms of how long that takes for it to go away. Usually about 10 half-lives, you're gone. Yeah, not too much left at that point. All right, so let's try a little kinetics here. Activity, if you have 1.35 milligrams of plutonium-236, calculate the mass that will remain after 5 years. Give you some info there. Our half-life of Pu-236 is 2.86 years. So let's see what you come up with. Yeah, you're doing so here. Anything that involves sort of how long something takes to decay and all that's going to be kinetics, and it's going again to be that first order kinetics. Which, if you want, you could just use the regular sort of first order equation. Don't necessarily have to use the nuclear chemistry version of it. And you also want to think about the half-life equation sometimes. They are oftentimes kind of used together, especially in these type of problems. And that is because if we sort of label up what we got going on here, we have an initial sort of concentration, if you will, of 1.35 milligrams. We want to know how much will remain at the end. So that's like your final concentration, which you don't know, after a time of 5 years. Now, if we look at our sort of first order equation, we can see that we have everything that we need except for actually a couple of things. We are looking for this guy. We do have this one given to us. We do have this one. But very common in these problems, you are missing the decay constant here. And that is where the half-life equation is going to come into play because we have the half-life given to us. So using the half-life equation, which is the natural log of 2 divided by the decay constant, we could actually solve for K, which is sort of missing here. And to do that, K would equal the natural log of 2 divided by the half-life. And I'm going to put this in, and that's going to give me the natural log of 2 divided by 2.86 years. That's going to be the natural log of 2 divided by 2.86. That's going to give us a K value here of 0.242. The units here are actually 1 over years. And by the way, for first order equations, the decay constant is 1 over seconds, 1 over unit of time, basically. So it's usually 1 over some type of unit of time. This is also where we want to make sure that our time, which is in years, and our decay constant, which is also in years, are the same units. It's very common as well that they are in different units of time, so you have to do some type of conversion sometime. In this case, we don't have to because they are both basically in years. So now we have everything we need to actually go in here. So the natural log of A, which is what we're looking for, would equal the natural log of our initial concentration, which is 1.35, minus our decay constant that we just solved for, 0.242. Again, 1 over years is the units. And that's going to work good with our, not 2, but our 5 years. This way the years will cancel out. So again, that's really important, those two guys in terms of those units, to make sure they agree. I'm going to clean up everything on the right-hand side of the equation. Basically going to take the natural log of 1.35 hit equals subtracted, open some parentheses, 0.242 times 5 hit equals. Going to give me a natural log of A is equal to minus 0.9099. Yeah. Any questions so far? To get rid of the natural log, we got to take the E of both sides there. So we're going to E this guy, and we're also going to E this guy with whatever sign it may have. When we do that, those guys go away, and we end up with A. And in this case, we end up with, I'm not going to use the rounded number, I'm going to use what's in my calculator. And we end up with something like 0.403 off of the non-rounded number. And the units here would be the same units as our other guy, which would be milligrams in this particular case. First off, any question on the calculation? Does make sense because at the end of 5 years, this thing's decaying. We should end up with less than what we started with, right? So again, if we ended up with more than what we started with, something not so right in terms of the math. And it's about 2 half-lives, I guess, it went through maybe-ish, or just under that. So if you divide it by 2.6 and divide it one more time, just less than that. Second half-life, we're in the right ballpark, probably. Yeah. Any questions on that one? All right, then why don't you try the next one and see what you come up with here. Let's do a little radon 222. Assuming no loss from leakage, if there's 10.24 grams of it in the house today, how much will be there in 5.4 weeks? And the half-life is 3.8 days. Let's see how we're doing here. So again, we're going to use our kinetics equation here. So once again, our two that, again, oftentimes will kind of go together is our first order, and then obviously our half-life here. We're going to run into kind of the same situation as we did on the previous one. We're going to have enough information, but we're still going to be really missing our decay constant in this case. We do have our initial concentration of 10.24 grams. We are, again, looking at basically how much will be there when it's all said and done. In this case, our time is 5.4 weeks. And again, we have the time, we have that, we are looking for that. So once again here, we are missing our decay constant. So that is where the half-life is going to come into play. We do have some unit issues here. We have this time in weeks. This one's in days. At some point, you got to do a conversion So I'm going to leave this in days, but I'm going to convert my weeks into days so everybody's on the same units. Again, if you did not do that, then you're going to be off because your units won't be the same. So I think still in 1 week, there should only be 2 days. No, there's 7 days, I think. So if we convert our 5.4 weeks into days, looks like we got like 37.8 days. So now both of my units of time are in the same kind of unit, so I'm okay. Again, if you did weeks, you'll have slightly different numbers, but at the end, it should really be the same-ish answer there with some rounding and maybe a little bit different. So solving for decay constant be the natural log of 2 divided by our half-life, which in this case is going to be 3.8 days. That's going to give us the natural log of 2 divided by 3.8. That will give us a decay constant of 1.182. Again, the units here are really 1 over days or reciprocal days, however you want to do that. Now that we have that, we're good to go back into this equation. So natural log of A is going to be our natural log of our initial 10.24 minus our 0.182, basically 1 over days, and that's going to be times our 37.8 days. And again, this is why the units are important, that they are the same, so everything cancels out correctly. So cleaning up the right-hand side here, 10.24. Natural log 10.24 minus 0.182 times 37.8. Going to give us a natural log of A is equal to minus 4.553. At this point, we're going to take the E of both sides here, and that's going to cancel those guys out. And again, we're not going to change any signs or anything like that. It's just going to leave it the way it is, and we'll call it 0.011 grams in this case. Any questions on that? That is less than what we started with, which I guess is good. Yes, I suppose in that case. Any questions on first order kinetics or half-lives or any of those things there? All right, then let's talk a little bit about, we could also use sort of our kinetics here to figure out, this one we just did, yep, okay, wait, there's another one. We can also use it for things like radio dating, or radioactive dating, by basically figuring out, for example, how much carbon there that we had, how much nitrogen may be left over. In the case of uranium dating, we could figure out, basically how much lead we have from there as well. We could still use our regular sort of kinetics equations to figure out, how old something is. We would be solving for the time usually in that kinetics equation. So a lot of times if you're doing some type of radio dating, you would use your first order kinetics, and usually if you want to know how old something is, that would be what you would be solving for. Again, just like the previous problems, you will oftentimes be using these guys here together, as you might be missing the K as well. So let's take a look at one here and talk about sort of how to approach this. An agent skull gives 4.5, and the units there are actually disintegrations per minute per gram of carbon. So it's actually a rate of radioactive decay is what we're looking at there. It's actually not Celsius there on the bottom or anything like that. So it's actually disintegrations per minute per gram of carbon, which is a rate of radioactive decay. And as I mentioned earlier, you could still use your kinetics equation with things like radioactive rates of decay in there rather than say molarity or grams and stuff like that. A living organism gives 15.3 disintegrations per minute per gram of carbon. We're looking to figure out how old this sort of skull is. The importance of this is it is carbon, so we actually want to use the half-life for carbon that we saw on the previous slide there, I think we might have it here or not. It is right there. We would want to use 5730 for our half-life in this case. So if we did this, we would still approach it the same way. We're going to use our first order kinetics equation. We're also going to perhaps use our half-life equation. And in this case, we have a couple of things. We have an ancient skull, so that's kind of like the dead guy, right? So that's the end of the road. And a living would be kind of like the beginning of the road or the initial there. And again, here we are looking for how old this thing is, so we're looking for time. So we are missing our decay constant in this case. So we are going to use the half-life there of carbon 13 or 14. And we're going to solve for K. So K in this case would be the natural log of 2 divided by the half-life. And again, because it says grams of carbon in the units there, that is how we know we should use our carbon's half-life. And if we do that, we get a natural log of 2 divided by 5730. Going to get us 0.000121. The units here are 1 over years. And now that we have that, we do have everything that we are looking for in this case, except for time, which is what we're trying to find out, which is how old this guy is. So the natural log of our final spot there would be our guy with our smaller disintegrations, equals the natural log of 15.3, which is our initial, minus our K of 0.000121 reciprocal years. And again, here we're trying to figure out how old everybody is in this case. Me personally, when I would do this is I would just simply take the natural log of 4.5, hit equals, and then I'm going to basically subtract this guy to the other side. So I'm going to subtract the natural log of 15.3. And when I do all that, I will end up with a negative 1.2238 equals minus 0.000121 reciprocal years in my time. At this point, all I have to do now is divide everybody over here, including the negative sign. So we're going to divide 0.000121. Going to give us a time of 10114 years old. That's pretty old. That's about 10,000 years old. So I would say that would qualify as being ancient. Yeah, in this case. So this, again, you can use that sort of rate of radioactive decay in this equation. You could really use anything as long as these units are the same. So it didn't really matter what they were, but they were the same on both sides. You obviously cannot use two different types of units on both sides. They got to be the same unit. Any questions on that there? All right, I did one, you do one now. So I want you to do the next one. I think we're looking for how old is a piece of rice that was found somewhere, I think, in this case. Let's take a look at it here. There it is. So we have dated the civilization to 15,600 years ago. If a living sample gives 20 counts per minute per gram of carbon, again, that's another unit of radioactive decay. What would be the number of counts per minute per gram of carbon of a rice that was found on the site here? So again, since it is carbon, we're going to use the same half-life as we used in the previous problem there, which again is our 5730. So we're looking for how many counts per minute per gram of carbon will this really old piece of rice give? Okay, let's take a look. So here we have something that's really old. We want to know what kind of counts per minute our radioactive decay is it going to give. So in this case, We are going to use our kinetics equation here. And since we've had to use it for the other ones, I anticipate we probably will still use it here, the half-life equation as well. All right, so in this case, we are given the time, which is 15,600 years. We are giving a sample that's living, so that seems like initial. And we are looking for what the counts per minute will be, which is our final. So once again here, we do need to count our K, and it will come out the same as the previous problem, as it is still carbon, and we're using the same half-life, obviously. So our K here, once again, will be the natural log of 2 divided by 5730 years. And I believe that was 3 zeros and a 121, I believe, if I remember correctly there. All right, so now that we do have K, once again, we could clean up everything on the right-hand side. So that's going to be the natural log of A is equal to the natural log of our initial counts per minute per gram of carbon, which is 20, minus our K that we found, which again is reciprocal years, and the time in this case, 15,600 years. We're okay in terms of units. Again, we have them in the same unit, so that is always a thing that you want to look at. So we're going to do a little natural log of 20, hit equals, minus it, open some parentheses, 0.000121 times a 15,600. Going to hit equals, going to give us the natural log of A is equal to 1.108-ish. We're going to get rid of the natural log of both sides once again by taking the E of both sides. That means that we will end up with, and I'm not going to use the rounded number here, I'm just going to use what's on my calculator, approximately 3.03. The units here will match the initial units, so these would be counts per minute per gram of carbon. Or I guess you could just write counts per minute per gram of carbon as well. No. That is less counts per minute than we started with, which should be good, right? Because as something is decaying, right, it's sort of dying in that sense. It's not going to be given off as much, obviously, radiation at that point because it's gone through several half-lives perhaps. So the counts per minute per gram of carbon should be less than obviously what we started with. Any question on kinetics type of questions? Now you should be able to answer how old your in and out double is on the exam next week, and we should be good, yeah. All right, any questions on that there? All right. So next thing we're going to talk about is fission, and fission is the process where a sort of unstable nucleus will continue to basically fall apart, if you will, go through decay, and it will form two new nucleuses. And the process of that usually is this guy will kind of fall apart into two new nucleuses, will also give off some neutrons, and a lot of energy is usually the process there where something will be given off. So during nuclear fission, there is sort of a slight difference in the mass of basically the nucleus of the new guy and basically the protons and neutrons that make it up, which are the nucleons. So there's a slight mass difference between basically the protons and neutrons that make up the nucleus and what is formed as a result of sort of the fission reaction. And that slight difference in mass gets converted into energy really through our good friend Einstein and his equation, E equals mc squared. That is energy, that is mass, and that is the speed of light, which is 3 times 10 to the 8 meters per second in this particular case. So in our case here, what we're going to talk about is what is referred to sometimes as the mass defect. And that mass defect is that little bit of mass that gets converted into energy in this process. And in a fission reaction, it obviously gives off way more energy than any sort of exothermic chemical reaction. So as you can see, there's a fission reaction, for example, like what they use in, say, nuclear power plants, give off somewhere by 10 to the 13 joules of energy. As a comparison, your really super exothermic reaction is like 10 to the 6 joules of energy. So there's a lot more energy given off in a fission reaction. Now, that mass defect, as I mentioned a second ago, is again, really the mass is going to be kind of converted into energy through this process. And the energy that's released when we do form that nucleus is sometimes referred to as binding energy or nuclear binding energy. And there are a couple of conversions here that can be helpful when we do these type of problems, and they're really kind of based off of the E equals mc squared. You could actually use kind of the conversions, or you could use the Einstein equation there. 1 mega electron volt is equal to 1.602 times 10 to the minus 13 joules, and that is your sort of conversion between two very common units of binding energy. So binding energy a lot of times is given in mega electron volts, or is given in joules, and those are two very common units that are used. It's also a lot of times given in mega electron volts per nucleon or joules per nucleon, which is a measure of stability. So sometimes people use binding energy per nucleon, and you could use it as a measure of stability. The higher the binding energy per nucleon, the more stable something is. 1 AMU mass defect is equal to 931.5 mega electron volts. That's another sort of conversion. And again, you could either do it kind of through the conversion way, or you could use the Einstein equation, and they both will give you kind of the same answer. You usually will end up in sort of joules if you go this approach. You'll oftentimes obviously get to mega electron volts here, but you can also get to joules as well using that conversion if you wanted it. So let's take a look at sort of what we're talking about here. So the nuclear binding energy, again, is that energy is required to break up a nucleus into its components. So if we took something like fluorine 19 here, it has basically 9 protons, as you can see there, and if we take 19 minus 9, will give us 10 neutrons. So the first thing that we could do is actually calculate the mass defect here, and if we have this fluorine 19, and it has an atomic mass of, we'll call it 18.9984 AMU, atomic mass units. If we were to calculate the mass defect here, we would take basically the 9 protons and we would times it by the atomic mass of a proton, which is 1.007825 AMU. We would then add it to 10 times the atomic mass of a neutron, which is 1.008665 AMU. We would then actually subtract it from the fluorine 19 atomic mass of 18.9984 AMU. So we're basically taking the mass of all the protons, taking the mass of all the neutrons that are in the nucleus, which is basically the nucleon, and make up the nucleus, and we're subtracting from the atomic mass of that isotope. And if we do that, we will end up with here. We will end up with a mass defect of 0.1587 AMU. That is the basically difference of mass between basically the protons and neutrons that are in the nucleus and the mass of the actual isotope itself. That little mass there is going to basically be converted into energy through this process. And again, at this point, you have a couple of things you could do. You could use E is equal to mc squared. And if we did that, our mass would be our mass defect in this case. This gives you 0.1587 AMU times 3 times 10 to the 8 meters per second, and that's going to be squared. And if we do that, we will end up with here 1.43 times 10 to the 16. My units here are actually AMU per meter squared divided by second squared. One relationship that you might remember is a joule is equal to a kilogram times a meter squared divided by second squared. So that is the same thing as a joule. We are almost there, except that we are at AMU and not kilograms. So you could take this and do a conversion to convert us into kilograms. And we can use our good friend, Mr. Avogadro, perhaps, yeah? So that's going to be 6.022 times 10 to the 26 AMU is a kilogram. Avogadro's number is to the 23rd. Yes, to the 26 gets you kilograms, to the 23rd gets you grams. Yeah, so that's why it's to the 26 here. And that will get us the AMU to cancel out. And if we do that, we will end up with 2.37 times 10 to the minus 11. And that would be kilograms meter squared second squared, which is the same thing as a joule. Any questions first off on that there? Now, that would be technically the binding energy, but typically it's given, as I mentioned, in joules per nucleon or mega electron volts per nucleon. So basically, a nucleon is the protons and neutrons. I guess that's a fancy name for mass number. Yeah. So we're going to basically take this and divide it by 19 nucleons, which is basically its protons and neutrons. And if we do that, it will give us a binding energy of 1.25 times 10 to the minus 12 joules per nucleon here. Any questions on that there? Now, if we wanted to, we also can convert this into mega electron volts at this point by using that conversion that there is 1.602 times 10 to the minus 13 joules per 1 mega electron volt. And if we wanted it in sort of the other unit that's commonly used, we could do that, and we'll get something like 7.791 mega electron volts per nucleon here. So those would be the answers in both units. First off, any question on that calculation? Now, we could, if we wanted to, just straight up use those conversions rather than Einstein's equation. And those conversions I'm talking about, which were on the previous page, we could have actually just picked up with our AMU, which was 0.1587 AMU. And we could have done that 1 AMU is 931.5 mega electron volts, which would have gave us 0.1587 times 931.5, gave us 147.8 mega electron volts, which if we divided it by 19, will get us 7.780 with rounding, a little bit different, but pretty much the same number as kind of what we got going on down here. So a little bit different with rounding, but you could have went that approach. And obviously at that point, you could have converted it to joules as well by using that conversion. So there's a couple different ways you could do it. Some people like to use those conversions rather than having to use Avogadro's number to convert it out, but they both will give you the same answer. Slightly different, obviously, with a little bit of rounding that you do, but pretty much the same answer. Any questions on any of that? And again, this is a measure of stability. The higher this number is per nucleon, the more stable that nucleus is. So that's another way, in addition to the N to Z and the even and even, that you can kind of measure stability if you're comparing to nuclei together and want to see which one's maybe more stable. Any questions on that there? All right, so why don't you try one then, maybe? Actually, we'll look at it this one first. So as I just mentioned, the greater the nuclei, nuclear binding energy per nucleon, the greater stability. And it actually peaks out right there at iron. 56 is actually the highest in terms of stability. And most of our stable nuclei do fall in this range in terms of binding energy, and kind of outside of that, fusion will get us into that more stable, or things will go through fission if they're outside that area to try to get them into this kind of stable area as we go through it. All right, so why don't you give one a go here, calculate the mass defect in the nuclear binding energy in mega electron volts per nucleon. Now let's do both, and joules per nucleon. And I'll give you your proton mass is 1.007825 AMU. And your neutron is 1.00865 AMU. All right, so calculate the binding energy per nucleon in both ways for our carbon-16. Carbon is still number 6 on the periodic table, hopefully. Okay, let's take a look. So again, we're going to figure out protons, neutrons, as we need to figure out our mass defect. So we do know, obviously, we have 6 protons here. Our mass number, which is 16, minus 6, which is our atomic number, gives us 10 neutrons. So we could calculate our mass defect here by basically taking 6 times our proton mass plus 10 times our neutrons mass, and we want to make sure we don't forget to subtract it from the actual mass of our isotope, which I forgot to do a second ago. All right, so if we do all that correctly here, we will end up with looks like a mass defect of 0.1187. Again, this is going to be converted into energy. And again, as I mentioned, you could go into Einstein's equation, you could use the conversion. So since we're going to do both units here, I'm going to just roll with the conversions here. So 0.187 AMU. 1 AMU there is going to be 931.5 mega electron volts. So that will directly convert me into where I want to be, maybe. That's going to give me about 110.6 mega electron volts, which at this point I can divide by the nucleon, which is really our mass number, which is 16 in this case. And that would get us to basically 6.913, we'll call it, mega electron volts per nucleon. First off, any questions on that calculation there? Once I have it here, since we're looking for joules as well, I'll do that conversion, just convert it out from here. And in this case, 1 mega electron volt is 1.602 times 10 to the minus 13 joules. And that's that conversion we saw on the other page. So if I do that there, going to give us approximately 1.11 times 10 to the minus 12 joules per nucleon. Yeah. And this guy. Any questions on either of those? Again, you could have obviously went into equals mc squared, then divided it by Avogadro's number to the 26th, which would get you to joules. You then could divide it by the nucleon, which should get you there, and then obviously you use a conversion to go from there to there in that case, yeah. Any questions on that there? All right, one last one to finish out the day here. Happiness, last example, yes. All right, let's do it. All right, here we go. Let's do our, we'll use those numbers there. Calculate the binding energy per nucleon for iron 56. We'll just do mega electron volts per nucleon here to finish it up. And iron, I think, is still 26 on the periodic table, I hope. Okay, again, we're going to start with our mass defect and our protons and our neutrons. So the atomic number here obviously would be our protons. We're going to take 56, which is the mass number, minus 26, gives us 30 neutrons in this case. So starting with our mass defect here, we're going to, and sometimes it is abbreviated, which like a delta symbol sometimes, and obviously sometimes just an M. We're going to take our 26 times, we'll use the number that's in this problem here, 1.00783 AMU, plus 30 times our neutron, 1.00866 AMU, and then we're going to subtract it from 55.93494 AMU. That's going to give us a mass defect, which again is going to be that mass that's going to be converted into energy through this process. And we're going to get here. Looks like 0.5284 AMU, which since we are looking for a mega electron volts, so might as well just again use kind of the conversion part of it. And that's going to give us 1 AMU is 931.5 mega electron volts. So we will times that by 931.5, going to give us a 492.2. We're going to divide it by the nucleon, which in this case is really the mass number, which is 56 nucleons. Going to give us a binding energy of 8.790 mega electron volts per nucleon. First off, any question on the calculation there? All right, so to finish up on, as I mentioned, we can use our nuclear energy, binding energy per nucleon as a symbol of stability. This is iron 56. Earlier we calculated a second ago 6.913 mega electron volts per nucleon for carbon 16, I think it was, and originally we did 7.780, I think, mega electron volts per nucleon for fluorine 19. The one that's the most stable is iron 56, just like we saw on that chart. It has the highest nuclear binding energy per nucleon. In this group, this guy would be the least stable of those three because it has the least nuclear binding energy per nucleon. Any questions on that there? All right, we're going to lay it up there for